All right, so today we're going to be talking about the integrated rate laws. But just to back up and give some context, when we talked about the differential rate laws, like the format of rate is equal to K times concentration of A raised to the M and so on. The differential rate law is our method of relating the concentration and rate, right? Determining what the rate would be based on the concentration. The integrated rate laws is based on your time and concentration relationship. So depending on the data that you have, one method would be more appropriate than the other. Okay? So let's consider this reaction here. I've got methyl isonitrile is converted to acetonitrile. And so essentially what that means is we have this molecule with a methyl group that's bonded to nitrogen that ends up changing the atom that it is bonded to. Right? So in other words, we get a flipping of sorts. Okay, so we collect data for this, and because this is gaseous, and we are collecting the CH3NC. I'm sorry, that's the pressure of the reactant. We're graphing the pressure as this reaction takes place, and obviously you can see the pressure goes down as the reaction proceeds along. We have less and less and less of the reactant. Right, which is expected. We talked about why this is. So with kinetics, with integrated rate laws, what is going to be most useful to you is a linear plot. And so with a lot of experimental lab data, if you can produce a linear plot from your raw data, it's going to be much more useful, and it's going to simplify the calculations greatly. So we are able to do this by taking the natural log of the pressure values. And by doing that, we straighten out the plot. All right, so we got a linear plot. So now that we've taken the natural log of our data and we've produced a linear plot, we got a straight line, and when this happens, this is confirmation that this process is first order. Okay, and so that should be jotted down, right? So when ln of the concentration or the pressure, right? I should say versus time, produces linear plot, that's confirmation of first order. Meaning rate is equal to K times A to the 1. Additionally, the K value, the rate constant, is the negative of the slope, is the opposite of the slope. So the slope of this line right here, right, m is equal to the opposite of the rate constant. So by doing this, you are both confirming that this is first order, and you are obtaining what the rate constant value is. So clearly you see the slope is negative, so the opposite of a negative slope means you get a positive value for the rate constant. All right? So if you look closely, because we have a straight line plot, this can be interpreted as y equals mx plus b, right? Slope-intercept form. and this should make sense because, again, look at your plot. Your y-intercept. Your y-intercept is your initial concentration. The slope is the opposite of k. Your time is the x variable, and the actual value that you're trying to obtain would be your final temperature, or your final concentration. So, depending on the data you have, you can go ahead and plug this data in. Now, an alternate form of this is if we were to rearrange the equation, right? And then we take if we subtract and rearrange to take the initial concentration over the final concentration, then we can go ahead and use our second form. But this actually, when I say second form, this is actually the first form. This is actually what we call the integrated rate law right here. Both equations are the same thing. They're just rearranged. Right? And both are perfectly viable to solve for any kind of problem that involves concentration and time, as long as you know that it is first order. Okay? And again, so I stress only first order reactions. So, a little bit of application. Sucrose in acidic solution breaks down into glucose and fructose. Do you guys remember sucrose being a disaccharide? Right? And so disaccharides are digested, broken down to monosaccharides. The monosaccharides, like glucose, is what's actually processed. It's undergoes respiration in your cells, right, to produce energy. This is a first order reaction, and the rate constant is provided to us. If we start with a 0.4 molar, that should be capital M molar solution, what will the concentration be after 18 hours? Okay, so they have told you this is first order, so we're going to use the integrated rate law. So the natural log of A sub naught over A sub t. By the way, this is on your formula sheet that the AP test will give you. All right, you just have to recognize this as the first order rate law. All right, what's concentration going to be after 1.8 hours? So they want this. Okay. So we've got to rearrange, right? First of all, we're gonna unnatural log. I don't know if the right word is, that's not the right word, but you guys know what I mean. So let's and then this is going to be our approach. Be careful though, because your time unit, look at your rate constant, right? Your rate constant is offering you a unit of per seconds, or in other words, 1 over seconds. So that means any time unit provided to you must be converted into seconds in order to proper cancel. So 1.8 hours, an hour is 100 seconds. So what is that? 6480 seconds. All right, go ahead and plug and chug. Let me know what you get. What's our new concentration going to be? understand how to check this. If you're starting with a 0.4 molar concentration, you should understand that your final concentration should be lower than the original, because we are plotting the concentration of the reactant. So who's got a value for me? I see you chugging away on your calculator. You got a value?
0.267.
Yeah. All right, that's A sub t. Okay. So some minor logging, to do in some of these problems. Nothing too bad. All right, so second question. How long will it take for the concentration to drop to 0.2 molar? So now the question has changed. They're asking what you're solving for time now. And you're going from A sub naught, which is 0.4 molar, to A sub t, which is provided as 0.2 molar, right? And time is in question. So if we were to take the ln of the initial, which is 0.4, over the final, which is 0.2, and that is set equal to k times t, you should recognize this as the ln of 2. And so the ln of 2 over k is how we find the time. This is actually the formula for half-life. ln of 2 over k. But then again, remember, only for first order. And I'm not going to say that you should memorize this, because really there's absolutely no need to memorize this. This equation, right, is given to you. So if you just plug in what your initial and final value is, you will have this equation no matter what. So no need to memorize it. Just be able to execute it. All right, so what is k? K is told to us to be, so we have the ln of 2 over 6.2 times 10 to the negative 5th. All right, ln of 2 is 0.693, so okay. And you're looking at about 11,200 seconds or so, which is an unwieldy value for seconds, so you might as well convert to minutes. So you're looking at about 186 minutes, roughly 3 hours. Okay, first order integrated rate law, a relationship between concentration and time. Right, the math end is not so scary, right? Be able to rearrange the equation and solve for whatever variable here is necessary for whatever the problem is asking. Okay, and again, I stress that this is first order. If the reaction is not first order, then we have to apply a different method. Okay, so note that for first order reactions, half-life is inversely proportional to k, and it is independent of the initial concentration. But, again, that's something you have to memorize because it's plain to see when you look at the equation. Let's talk about a second order reaction. Second order reactions. In a second order reaction, the concentration change is dependent on the initial concentration. And so your integrated rate law, you know what? Sorry, I'm going to jump down here first, and then we're going to go over that. in this example here, we have our time. No, sorry. That's not time. Time's over here. We got our time. And we've got our concentration. And we have a plot of our inverse of concentration. So for second order reaction, if the inverse of the concentration versus time produces a linear plot, that's conformation. So imagine, let's say you have some raw data. And let's say with that raw data, you plot it and it gives you a graph that's not straight. Let's say you take the inverse and it's not straight. So then if you take the if you took the natural log and it's not straight, but if you take the inverse and it is straight, that is conformation of second order. And in this situation, k is equal to the slope. Okay, so let's back up a second. If we can rewrite this equation in slope-intercept form, right? Whereas we have y, m, x, and the intercept. Okay, so practical application of this. Let's say we have NOCl decomposing to form NO and Cl2, right? And it is known that this is a second order reaction. So we're going to use our second order integrated rate law. Here's what we know. K, the constant is known, the initial concentration is known. What will be the concentration after 30 minutes? So it's A sub T that we're trying to find. Okay, so our constant, 0.020 liters per mole second. Our time is 30 minutes, but 30 minutes needs to be in seconds, so 30 minutes is 1800 seconds, plus the inverse of our original concentration, which is 0.05 moles per liter. Okay, well, if we kind of just simplify this a little bit, 0.02 multiplied by 1800 is 36, and if you pay attention to the units, the units are inverse molarity, liters over moles, plus 1 over 0.05, which is 20. And if you take 1 over moles over liters, the unit that results is liters per mole. Right? Because these have like units, they can be added. So we're talking about 56 liters per mole is equal to 1 over the initial or the final concentration. So final concentration then who's got my final concentration here? Angela?
0.01785.
Yeah. We'll go with 0.018. Oops. 0.018. Okay. Second question, how long will it take for the concentration to reach 0.01 molar? So they're asking for time. How long will it take? Okay. Well, since both concentrations are known, we can just go ahead and use the same equation, plug in what we know, but this time we're solving for time. So 1 over the final concentration, which is 0.01, is equal to 0.020 liters mole second times the time plus 1 over the original concentration, 0.05 moles per liter. Okay. Take a second, figure out how long that's going to take. All right. Someone else give me a value here. Yeah, Zoe, what'd you get? 4,000 seconds, yes. 4,000 seconds, or roughly 66 and 2/3 minutes. Okay. So, second order integrated rate law, right? This is provided. This is on the formula, the AP formula sheet. You just have to look at it and recognize what it's for. Okay? Again, relationship between concentration and time. There's no natural logs involved here. It's just strictly an inverse relationship. Okay, well, what if there's a zero order reaction? A zero order reaction, here, let's refresh what these mean, right? So remember how if it's a first order reaction, that means double the concentration equals double the rate, right? If there's a second order reaction, that means if you double the concentration, the rate quadruples. So zero order reaction means if you double the rate or double the concentration, no effect on rate. Zero order reactions are not affected by what the concentration is. And as such, a plot, well, that's not very straight. A plot of a concentration versus time, if the concentration plotted versus time is linear, that is evidence of zero order, right? And if that's the case, that simply means then the rate is equal to the rate constant, because the concentration taken to 0 is just 1, so rate is equal to k. Therefore, you can solve for the final concentration simply by taking the initial concentration minus, however much would have been reduced by the time. So the rate, the constant times the time. The half-life of a zero-order reaction does depend on the initial concentration of the reactant. right? So, which kind of makes sense. You know, how long it takes to cut it in half depends on how much was there at the beginning. So, to summarize, we're only going to really be paying attention to graphical interpretation of 0, first, and second order, right? Your differential rate equations look like this. This shouldn't be any surprise. The integrated rate laws we just went over. So first order natural log of initial over final concentration is equal to KT. Second order is the inverse relationship, right? This is just rearranged. And if it's 0 order, right? For 0 order, then the rate constant multiplied by time is how you're going to find the difference between the initial and final concentrations. These you don't have to memorize. These are on the formula sheet. But what you do need to know is you need to know how to get the straight line plot, because the straight line plot is the usable information from the graph. So again, natural log of a concentration versus time is how, if that's a straight line, that means it's first order. Inverse of the concentration versus time, if that's a straight line, that means it's second order. And if just regular concentration versus time is a straight line, then it's 0 order. How do we find the rate constants? Well, it's the opposite of the slope for 0 and first, but it's just the slope value for a second order. Your units on K, I'm not going to say you should memorize this because you can very simply solve for what the units of K are, right? But I don't know if you've noticed so far, maybe you haven't done enough problems, but whenever something's first order, the unit is usually inverse time. And let's specify this 1 over time, not seconds, because it's not always seconds you're using, it could be minutes. Right? So it could be minutes to the minus 1, right? Okay. So I've got some raw data here, and we need to determine if this is a first order or second order. Whenever you have raw data and you need to figure out what order it is, you have to plot it. So bust out your calculators, head on over to your stats button and start entering your data in and seeing which plot, the inverse or the straight up, the inverse or the natural log gives you a linear plot. So as you enter this in, couple of tips. In your list, when you enter in your list data, L1 is the X values by default, right? So time. L2 is your Y value. So what I did was I entered in L2 the concentrations, 2.08, 1.67, and so on. L3, in order just to quickly calculate all the values for L3, what I did was I highlighted L3, and I just typed in ln of L2 and hit enter. And it calculated the natural log of all of the values that I entered in list 2. And then for the fourth column, I highlighted L4, and I just entered in 1 over L2. And that took the inverse of all of the L2 values. And so when you look at these on your graph, probably with only 4 points, it's going to be hard to tell if this is linear. So the better thing to do is to calculate the linear regression. So calculate the linear regression of L1 versus L3, right? Because remember, that's the ln one. And then do L1 versus L4, which is the inverse. But in order, you're going to get a slope, but the best way to tell which one it is, you need to turn on your diagnostic on your calculator, and that's going to give you your R and R squared values. I don't know if you guys know how to do this from math class here, but just kind of follow with me here. You're not going to lose anything. See the catalog button on the bottom of your calculator? Right, so it's a secondary function, so hit second catalog. And then it should say catalog, the whole list of different functions. You want to scroll down until you get to what's called diagnostic on. There's a lot here, so just hold it down until you get to it. Diagnostic on. Hit enter twice. And now, whenever you calculate a linear regression on your calculator, or any regression for that matter, it's going to give you the R and R squared values, and you're looking for R squared values that are closest to 1. Whichever one has an R squared value closest to 1 means that that's the most linear, and that's the one you should choose. So back to our calculations. So I've got my calculator. I'm going to go to calculate linear regression, and I entered in my X list L1, my Y list L3, and hit calculate. And so not only do you get Y and A and B values, but you also get R squared and R equals value. And so my R squared for this is 0.99, which means this is the most linear. You could also look at the graph, but with only 4 points, it's hard to tell by looking at a graph with 4 points which one is more linear than another. If you guys need help with this, it might have been a while since you graphed this on a calculator. We can practice more of that. That's no problem. Okay, so in graphing this, we determined that this is first order because it's the natural log that produces a straight line, and our slope, which is the opposite of the k, so the k is going to be 0.0375. And your units were 1 over minutes. Okay. I'm going to stop this recording here now and just check in with you guys.